Alright, hell yeah. We got material mechanics, and I have one more problem in me tonight. You know what I mean? I think we can do it. And so, this is a 1-star problem, so hell yeah. And it's elastoplastic problem. So, I guess I don't want to read it. But what because we got to do more of the who cares. I keep forgetting about that. You know what I mean? It's just like, how do you take a problem and be like, well, who the hell cares? And basically, they want to kind of know. I guess just go right to the question. Determine the max force P that you can put on these two cables. And knowing that you're going to have a plastic, you're going to take one of these cables to their limit until the other cable gets right to the limit. If you take them both to the limit, it's just going to turn into Play-Doh and break. You know what I mean? So we're going to take it right up to that limit. Cool. So now, any problem, you just want to make the geometry just a lot easier. So we're going to take this P, and then we're just going to, like let's say we just had one of these cables, and we took the load P and we just put it right underneath there. Well, great. This cable is going to take like all the load. You know what I mean? I think visually you can see that. And if it's way out here, well, now you're just, or just way out here, now you're just making a leverage, you know what I mean? So if we go twice this distance, hell yeah, this cable is going to, whatever you're putting down with P, pulling down, this cable is going to take twice that. Okay, so now let's add the second cable and then still simplify it. Let's say these cables are fairly close together, and then we're going to put the load P right in the middle. Well, it looks like the force is going to be evenly carried by both those cables. Cool. So that would be the strongest place to put the force, but we know that the force is out here, so these cables are going to get hella stressed just a little bit more. And then what if you put the force like directly right there, just right over that pin? Well, guess what? These cables ain't seeing any of that force. So just right there, that probably blows your mind, because you probably aren't doing that at the beginning of a problem. You're probably just going for what they're asking and trying to tackle the nitty gritty. Okay, so, and then you can move this P like right here, and guess what? Well, some of this load is being taken by the pin. Like maybe half of it's being taken by the pin, and the other half has been taken by BC. So if both these cables can take like a hella force, well then this, the load P can be bigger. So the load P right here can be infinite, if that makes sense. Way the hell out here, the load can be very small. If you have a huge lever arm, it's just no chance. You're just going to snap those, whatever they are, cables or steel rods. But hell yeah, and then if the load is right in between, so that's the one that we're going to do. We're going to say, hey, and let's just, and this is one of those problems where it's just all letters, you know what I mean? So you're just like, this thing could be tiny. It could be the size of this paper, you know what I mean? That could be actual size, or it could be just huge industrial. So let's ramp it up. I'm going to say each of these cables is that kind of 1 square inch. I always go back to this just because I know the breaking strength of steel is 58,000. Now I should be memorizing the breaking strength of other materials, but this one is just really easy. I'm just going to write it in PSI this time. And what else do I know? I know that the stretch or strain, this is stress, this is strain. It sucks that they both sound the same, but strength and stretch is what I call them. That's going to be change in length over length. For steel, that's going to be 0.002. You know what I mean? Okay, so right now, if I have an area of 1 inches squared, and I know the material is steel, well, cool. I know that from this equation, strength is force over area. Rearranged for force is equal to strength times area. I know that the force is going to be 58,000 psi times 1 square inch, because it's pounds per square inches times 1 square inch. Cool. I know each of these cables can take 50,000 pounds. So that's in my book. I'm going to say, okay, I have at least, and there's 2 of those cables. I can't do that mental math. 58 times 2, 116. So both these cables, so P, if P was right here, P would be 116,000 pounds. Okay, so now when we actually do the problem, we can actually throw in this geometry, and what are we going to get? Well, we're going to get P is less than 106, and let's just guess. Let's just say P is probably, for this scenario, 90,000 pounds. I don't know, I probably undershot that. Okay, so now we can get into the nitty-gritty. So the first thing that you want to do is write your equations. Strength is force over area. Stretch is change in length over length. And again, this is strain. I call it stretch. This is stress. I call it strength. Okay, and then there's a relationship between stress and strain. And we might as well draw the diagram. You know, I mean, pretty much every time you want to do this, because what you do is you take a specimen of steel and then you pull it in a machine. You know what I mean? You put a force on it, both directions, and then you see its change in length. You know what I mean? Compared to this length knot, you're going to see a little change in length down there. And then what you're going to plot, and then you're going to say this force, and then this has a cross-sectional area. So you're going to say the P divided by A, and we're going to call that the stress. So we're gonna say PSI is on this side, and a dimensionless term of strain, of change in length over length, on this side. So this is force over area. But at the end of the day, it's very synonymous with the same graph that says, hey, what's the force applied and what's the change in length? Because I think those parameters, change in length, you could actually see. And force, we all kind of know force in pounds. And it's basically going to be the same shape, same graph. Okay, so hell yeah. And so let's keep writing the equations. So if I say on this graph that we have a strain, we observe a strain of 0.002, and that happens at a stress of 58,000 pounds, then I know that 58,000 PSI, I'm sorry, this should be PSI, excuse me. This is stress. This graph is a stress-strain curve. But this point right there is synonymous with 58,000 PSI is equal to 0.002. Now the units don't match, you know what I mean, worth a damn. And this number is big and this number is tiny. So how can these two numbers equal each other? Well, we have to throw in a constant here. So basically this says strength is equal to some sort of proportionality constant times strain. And that proportionality constant is modulus of elasticity. And it's the slope of this graph. So it says, hey, if you rise over run, if you're going to go up 58,000. So your rise is up 58,000 and then over 0.002. That's the slope of this. And so if we say this is E, and then we want to solve for E, well, hell, we take this downstairs, 0.002, and look at this. This is rise divided by run. We're going to go up 58,000 PSI and then over 0.002. It just sucks that this is a dimensionless number and this is in PSI. It would be fantastic if you took whatever specimen you were saying, and this is, if we had a 1-inch specimen that was 1 meter long, you know what I mean, let's say this is what we're pulling. We have 1 meter specimen and it's yeah, I mean, that's kind of weird that we have 1 meter and then 1 inch squared, but work with me. We're still going to get a 58,000 pound force, and we're going to have a change in length of 2 millimeters, which is 0.002 meters. You know what I mean? So that same 0.002 pops up because our length was just a unit length of 1 meter, and then so strain times length, it would be the change in length. So there you go. So now we have a graph that says force is 58,000 pounds, and that's All right, hell yeah. And that's going to be equal to 2 millimeters, you know what I mean, or 0.002 meters. And guess what? We need something, we need, this number can't equal this number, so we need some sort of constant, and that's going to be modulus of elasticity. Well, is it the same? Well, for that setup, this slope is also, you know, that would be confusing. But this slope m, so that's the thing. That's why you can take any specimen. Typically, you take like a 2-inch long specimen with an area of like, I don't know, just like 10 millimeters in diameter, just like 1/4 inch across or whatever, or less than 1/2 inch across, and then you pull on that. And then so why this graph makes sense for all materials made out of steel, because it says whatever your area given and whatever length you choose, you're going to have a ratio of force divided by area, that which is in psi. So it is cool because every molecule of this piece can only see 58,000 psi. And if you have a given length, even if it's just 2 inches, your strain can only be 0.002. So that would be a change in length of, well, you take that 0.002 and then multiply it by whatever length of your specimen. So if it's 2 inches, it's 2 inches times 0.002, and you're going to have 4 1,000ths of an inch. You know what I mean? And that's all you could stretch this before it starts to go plastic. If you stretch it up to this limit, well, cool. You can let go, and it's just every molecule is going to go back to its original location. All right, so hell yeah. But this problem does say, hey, we are going to stretch things into their plastic range. And anytime that you do that, you got to recognize that this, if you had a 1 meter specimen and you're pulling on it, yeah, you can pull on it 2 millimeters for this elastic range. But then it's going to go plastic. But how far can you go down this plastic range? Well, you know, up to 5%. You know what I mean? 5% of 1 meter is 0.05 meters, which is, you know, 50 millimeters. So you could stretch a 1 meter steel rod by 2 inches. And is that right? Because this is about 40 inches, and then 5% of that, 40 times 0.05, yeah, it's 2 inches. So you could have a 1 meter length of steel, and you could plastically stretch it 2 inches. So that's significant. And a lot of times you do problems, and you know what I mean. You're just stretching it like another 2 millimeters for your plastic range, but you're not realizing that you can stretch this up to, well, 2 inches is 50 millimeters. So there you go. All right, so let's start the problem, and I think that's a good intro, so we can keep writing these equations. Strength is force over area. Stretch is change in length over length, and then we have what relates them. Strength is equal to E times strain. So stress is equal to E times strain. So this is a monster number. This is a tiny number. Multiply big by small, and hell yeah, you get a normal number, which is kind of like the tensile strength or the yield strength. I shouldn't call it strength all the time, because it's either it's the tensile stress or the yield stress or the max stress. Okay, so stress and strain. Cool. So now we can put this equation, F divided by A, into that, and we can take this strain. We can put change in length divided by length into this equation. So let's do that. We're going to get F divided by A is equal to E change in length divided by length. And now we can rearrange this. And what I do is I get the equations that I want. Usually I want to know change in length. That's a good parameter. And I kind of want to know my max force. You know what I mean? So let's solve for change in length. That's going to be change in length is equal to L goes upstairs. So we got FL divided by E goes downstairs, EA. And then if I want to solve for force, you know what I mean? EA goes upstairs. So we're going to have, I'm going to do that first now. Change in length divided. I got to write this like this and then change in length, because the force of a spring is my other equation. Force of a spring says, hey, that's K times change in length. It's identical to this. So now we know that K is EA divided by L. So if we treat this like a spring, its spring constant is EA divided by L. Sometimes it's very useful. All right, but for this problem, you know what I mean, I kind of stopped there, but I shouldn't. You know what I mean? Once I put all these things together, you know, we can also rearrange a little bit. Well, I don't know. Well, let's save that for this problem and see what things come out of this problem. Yeah, that would be an interesting one. Okay, so let's do it. So what we're going to do is we have to draw a free body diagram, which is basically cutting this. And let's go a little slower now. You know what I mean? We're going to cut this out of outer space. And so we're going to draw that. And what I mean by cutting it out of outer space is like, hey, at this pin, we're going to have two forces. We're going to have a force AY. Any pin force, you're going to have two forces, AY, AX. Now this, if we pull down on this, we can be like, okay, these two ropes are supporting this loads. So we can have, we can have FC and then force B. And, well, I don't even want to do that. I just want to say C and B. So there you go. And then over here, oh, I guess we could do BY, CY. That'll make sense. And now right here we have P. Cool. So now we can, and what this means, why I said chopping it out of outer space, because if we know that we have a downward force, we know that this, visually, this bar is not moving. It's not flying through space in that direction, up or down or sideways, you know what I mean? So we know that it's not moving. So Newton's law says that force is equal to mass times acceleration. It says if you can identify a force, you know what I mean? Hey, be ready, because that object that you're identifying the force on that mass might have some acceleration. And but guess what? We are visibly not seeing acceleration. Acceleration is zero, but we observe a force. We know that there's a force. We put a force on it. So we actually did this side of the equation. So what gives? Well, it just means that we have no acceleration. So if we saw this force down, so if we saw like negative P, well, we can't have it we can't just have that force. We have to have some other forces to balance, and those are going to equal zero. So that's a pretty good explanation of why, hey, if you have a downward force, well, you better have an upward force. And if you have a force in this direction, you better have a force in that direction. But even look at that. Does that even make sense? Because if I wrote this pin connection with a force in that direction, well, what the hell would... And it's pushing that way. What the hell is pushing this way? Nothing. So even just visually, I can see that that's zero. I don't even have to do any magic, equation for that one. And then the other aspect of this is like, hey, if I have a bar and I have an upward force here, P, but then a downward force here, A, hey, let's say these balance, P is equal to A. So we're going to say that. But guess what? Unless P is directly right there, pointing at A, this thing is going to rotate. It's just obvious that if this was floating in outer space and you put two forces on it, it's just going to start spinning about its center of mass. But guess what? Eyeballs on this, we don't observe any spinning. So that's and you know what I mean? I guess that's not Newton's equation. But it just says, these forces induce a torque. You know what I mean? This is a moment arm where either this total distance, if P is equal to A, this total distance D, the torque is equal to P times D. Or it's equal to P times D divided by 2 plus A d divided by 2. And P and A are the same, so it's just going to be that. So we're going to have a net torque. Alright, hell yeah. So in this setup, we would have a net torque, and this thing, you know, and we use the right-hand rule. So if you have a force going that way and a force going that way, the torque's going to be, it just kind of shows that, hey, a positive torque is a counterclockwise rotation. But guess what? This isn't rotating. So we have to say all the torques that might be generated on this thing have to equal 0. So even right here, P and AY, you know what I mean? If we figured out what those were, those are creating a negative torque. And then, what else? Well, let's see, how would we do that? You know what I mean? You have two forces going up, and then a force going down, and then, you know what I mean? Well, obviously, if you look at it like that, they might balance each other, and they do. Obviously, that's basically what we're saying. So then, you know, every point on here, it's kind of an interesting thing. I actually don't know how to explain that in any other words than saying, I'll have to explore that one. But yeah, if you pick a point right there and say, hey, this is creating a torque. This is your distance, and this P is downward. But then, hey, this is your distance, and this BY is upward. And then this is my distance, and this CY is upward. These forces act right at this point. So if we just have this as our pivot point, you know what I mean? Oh, so that kind of explains it. Any free body diagram, I can take a pin, you know what I mean? I can stick this thing on a wall in outer space and then just pin it to outer space right there. And then, sure, it might rotate around this point, but guess what? We don't observe that. We observe from this position that, no, it's not rotating around a fictitious pinned point that you did. So I can put a pinned point anywhere. I can tack this thing into outer space, and I would still see no rotation, because just the forces on it are keeping it balanced. It's keeping it balanced in outer space in the Y direction and in the X direction, and it's not twisting. So sure, I could drill a hole anywhere in it and then pin it to outer space. It's not going to be a spinning like pinwheel on that point. So there you go. I think that was a really good. But that's why you always choose your pinpoint where you have like a lot of forces that you might not know. So you know what I mean. We want to know BY and CY, and we're gonna obviously apply P. We're gonna know that. So we're gonna take moments about A. So hell yeah. So we're gonna go. Let's get some fresh sheet of paper. I'm gonna rewrite these equations. Catch you on the flip side. Alright, hell yeah. So we're back at it, and we're going to sum moments about A. We got that. Sum moments about A is going to be 0. So we're going to have P. So we're going to have a downward torque. And sometimes you can just do this. You know, just like you would say well, let's do it for some of the forces in the Y direction is 0. We can say, hey, these two upward forces in the Y are going to be equal to P. So instead of saying negative P plus BY plus CY is equal to 0, you can just say P is equal to BY plus CY. You know what I mean? So you'll see this shortcut all the time. We can do the same thing with torques, moments about A. I'm going to say P times this distance is negative, and then BY and CY are positive. So I can just equate those two. So I can go P times 4B is equal to BY times 2B, that distance, plus CY times a distance of 3B. Cool. So, good to go there. And now we know the forces in the Y, so we have, you know what I mean, we have, we know what P is, and we have two equations, two unknowns. You know what I mean? So I can say right here that, let's just do BY. So we're going to go BY is equal to P minus CY. And then everywhere we see a BY, we can throw that in. So we can go 4PB is equal to, so this is going to be 2PB minus 2CYB, minus 2CYB. Plus 3 CYB. Cool, so we have negative 2 CYB plus 3 CYB. We're just going to get 1 CYB. And then over here we can subtract 2 of these, so we're going to get 2 PB is equal to CYB. And then the B's can cancel. So even just right now we know that P is equal to CY divided by 2. Hell yeah. And booyah. And hopefully I did that right. I feel like I munched it. But CY divided by 2. We can always double check that. But now we're going to throw it into this equation, and we're going to say that P Oh, so this is also saying that CY is 2 times P. Oh, so right there. And then we know that we apply a force P right here, this CY is 2P. And I swear it feels like I did something wrong. But we're going to throw this into this equation to get BY. So BY is equal to P minus 2P. Holy hell. Yeah. What did I do wrong? Okay, so we have, let's go back to our moment. Sum of the forces in the y, we're going to have P is equal to BY plus CY. Oh, did I not incorporate AY? That's probably right. Bummer. Yep. And I don't know what direction AY is. You know what I mean? I could just assume if I'm pulling down on this and this is kind of acting as a pivot point, you know, AY might be this direction. You know what I mean? So AY might be down. Holy Toledo. So I can't. Yeah. So that's why we have this problem. It's so let's do the sum of the moments about A again, and we're gonna have 4PB is equal to 2 BYB plus 3 CYB. Cool, and now we can get rid of the B's because those are all the same. So we can get, this is gonna say there's a relationship 4P is equal to 2 BY plus 3 CY. Alright, so now we're cooking. So now, you know, if P is, and we could divide by 4. So we could say P is equal to BY divided by 2. See, now this is making sense. Plus 3/4 CY. So just visually now, hell yeah. If I pull down on P, BY is going to be half. No, I apologize. If, we're kind of, oh shoot. No, whatever BY is, divide by 2, and then whatever CY is, multiply by 3/4, and then you get the total load. That's weird that even this is just like, what's going on? You know what I mean? Are BY bigger and CY is bigger? Sure they are. Oh, well, no. Let's go back to our basics. If we throw P right underneath these, you know, equally, then this CY is equal to P divided by 2, and this one's P divided by 2. You know what I mean? And then both those are going to equal to P. But in this case, so we would have, yeah. So that's what's happening. But in this case, we're going to, instead of having yeah, and that would be in that case. So yeah, so obviously, well, let's just throw some numbers at it. Let's say this was 2P. So we would, If this was 2p, it would be 2p divided by 2, and you'd already be at p. So this can't be 2p. But we could say it's is it half p? Because then if this was half of p, then we would have 1/4 p plus then this would have to be 3/4. This would have to be, you know, a total load of p. So if this was half, this would be 3/4. So it'll probably be somewhere right in between. And I apologize that even from the moment equation, it seems like you would have that check on reality, but I don't think you do. I think it's an indeterminate structure. You can only have one of these. When you pull down on this one, you have no idea if one of these is taking what percentage of the load each of these is taking, because I think it's an indeterminate structure. That's why elastoplastic problems, you know, appear in indeterminate problems, because you get that extra equation. And that extra equation, okay, so now we can just go for the problem. It says determine the yield load Py and the corresponding yield displacement at point D. So it does want to know, like, hey, this change, you know what I mean, this delta D, but we definitely want to know also the load Py that we can put on this. So how we determine that is we want to know the max. We want to know Cy max, and then we also want to know By max. Now, in material mechanics, there's two ways to do that. One is that we can put acronym. So we can't really change the area or the lengths of things. That's already given in the problem. But everything else can take a subscript. We can say, hey, this is max, this is max. We could say strain max, change in length max. So these two equations are the ones that we're going to be using. And so we can be like, oh, okay, I'm going to say I want to know the force max in this. And so I'm going to say force max, which is Cy max, is equal to this equation. Stress, yield stress times A. And that's what it says. It says write the equation, you know, or you could just do strength max times A. But know that that's going to be yield stress times A. So this, and these, if we read the problem, are probably same. Both wires have a cross-sectional area A. So cool, they're all the same there. So yeah, so the max force that C can take is this right there. And we're basically done. So Cy is equal to yield stress times area. Same thing with By. By, same equation. By is yield stress times area. You know, it's because the area is the same, and we're given the property of the material. All right, hell yeah. So now let's go for it. And so let's see. The other thing that we're going to introduce is the idea that these are going to change in length. So the max change in length is, you know, it's going to be the strain times L. But even in the problem statement, it doesn't give strain. It does give E. So, but when we put all these equations together, we can say, hey, look at this. The max change in length is going to be FL divided by EA. And this equation is where I ran into where the problem in the back of the book, you know what I mean? Well, there's this equation you can write. Look at this. This is F and A. So you can say that this equation is change in length, yield stress times L divided by E. You know what I mean? So there you go. I couldn't think of that at the beginning of the video, but like I said, as you're doing this, you're like, oh yeah, that's definitely a key equation. Because now we're going to say that the change in length of, you know, the change in length of this is this equation. And in this case, the length is, so let's do that. So we're going to do change in length of C is equal to the yield stress. L though is 3/4 L. So we're going to go 3L divided by 4E. So that's the change in length of C. The change in length of B is, well, that's just a length of L. So it's going to be, yield stress L divided by E. Okay. So now you know, we know that this is going to change in length more, and this one is going to change in length less. Cool. And we see that there's when we pull down on this, we're going to have this happen. You know what I mean? This bar is going to be at a triangle, and we're going to say which one can change in length less. So right here, I mean, this problem would be very unique if the shorter cable was over here. But even it's not a 2-star problem. You know, it's just a 1-star, and we can see that this shorter cable can't stretch very far. It can only stretch 3/4. And look at this. By geometry, this is stretching hella compared to that. Whatever this is stretching, well, it's not half, because if this would have to be halfway between the pivot and here. And so this is stretching, 2, and if it was over here 1/3, so it's right at the 2/3 mark. So if this stretch was 1, this stretch would be 1/3, and this stretch would be 2/3. So cool. So now we know that this length will, if this stretches the full 3/4, so we got 3/4, then this will stretch 2/3 of that. You know what I mean? So we just kind of want to get a visual sense of how much this one is stretching, and that'll be 2/3. We just multiply by 2/3, right? Heck yeah! And then we'll have 1/2. There you go. So that would be the change in length of B after this one's maxed out. Well, guess what? This chord's not maxed out. You know what I mean? So this is where the problem of plasticity comes in. Is when you pull down on this one, you're lengthening both of these chords. Now, once this chord is fully lengthened, its stress or its force can only be this number, the yield stress times the area. If you pull it farther than this one, you know, like down here, it can't take any extra, you know, it's not resisting any extra force. So the force in that one will just be that stress times that area. So that means, and this one still hasn't given. This one's still got plenty of elasticity. So yeah, maybe that's why it is a 1-star. Well, no, I should have through observation seen that. Well, obviously this one's going to go plastic first, but at that point this one's not going to go plastic. So what we need to do is change this length by this, so that by a full unit. So we're going to say, hey, this is 1 full unit. And that's what this is. This is 1 full unit. And when we do that, then what's the change in length of this? So now we have 1 full unit. This is 2 full units. So this is 1.5. You know what I mean? So if we change the length of B by this, the change in length at C will be 3/2 yield stress length divided by E. And 3/2 is definitely bigger than 3/4. So there you go. So obviously, yeah, this thing is maxed out and turned plastic. And once we get to this change in length, that's the point where this will turn plastic. So I like to work with change in length first before I work, because I think more people should work with, hey, these are springs and they can change in length up to their max. And so now that we know that the change in length here it's not 1, but it's yield stress length divided by E. So we know that the change in length over here is 2. So we know that delta D is 2 yield stress length divided by E. So that question is answered. And now we need to know how much load it takes to do that. And this is actually where the problem gets real easy. It doesn't seem like it does. And we're not going to draw the load displacement because I got to go to bed and stuff. But any plastic problem, and let's write our equation. We said that Cy, what the hell? Well, no, we can just do this out of the top of our head. You know, this is going to be yield stress times area. PSI times, pounds per square inch times square inches is the force. And then, so By is same thing, yield times area. And the cool thing about plastic is like, hey, it is just like saying force, just a constant force. It's like you're putting a constant force, so if you're pulling down past the plastic load of both those, these are resisting by, so hard to say, you know what I mean? I just say stress max area, but it's, or like breaking strength, but it's yield stress. So yield stress area. So now we can just do our free body diagram that, so we know that, and here we go. So here's AY, AX. And we're going to do sum of the forces in the y is equal to 0. So we don't know what, we designated AY up, but it might be down. You never know. So we're going to do AY plus 2, because there's 2 of these, yield stress times area minus P. That's going to be equal to 0. And then we're going to sum the moments about A. So now we have yield stress area times 2B. So from this point, these are positive, and then this one's negative. So plus yield stress area times 3B a distance. And then that's going to be, I'm just going to do equal, I guess, to P times 4B. Cool. So like right here, all the B's can just get drop out of the equation. And so we're going to have yield stress area, so 2 plus, alright, hell yeah, home stretch. 3 pops out in the front, 3 yield stress area, so hell yeah, we got 5, and then that's going to equal to P 4P. So we have 5 yield stress area is equal to 4P. So cool, now we got 5 force yield stress area is equal to P. So cool, now we know the force P. Max force P is equal to 5 over 4 yield stress area. And now we can do this real easy because we said that this change in length is FL over EA. And we're going to circle this, and we're going to say that sigma YL divided by E. And if that's the change in length of this one, by geometry, this one has to be twice that. So we can say delta D is 2 yield stress length over E. So it's interesting, like once you do the problem, going back and then being able to get there faster. But you know what I mean? After you sleep on it, it's still such a slow slog, to kind of put everything together. But when it does come together, then you find the quicker ways to do it. But at the end of the day, I've always said do this, change in length is FL over EA. But the cool part of this problem was circling this FA and saying, hey, change in length is yield stress length divided by E. That was a game changer. And then also just knowing that strength is force over area, that, hey, your force max is just yield stress area. So these were the 2 equations that I definitely will now put into my pocketbook. And those are the equations that I actually wanted at the end of the day. I just wouldn't write this like this. I would just say, hey, change in length is FL over EA, and force is equal to, well, this one you really can't change up too much. I mean, I guess, yeah. I mean, well, you could say that there's a relationship between this and strain, and then so you could throw in E this A, and I do that because this is force E change in length A divided by L. I don't write it like that. I write it force is equal to, well, I used to write it like this, change in length EA divided by L, but no, it's a smarter way to write it with EAL as a package unit right there, and then change in length. And these are given parameters. Like, hey, you're given, the problem already shows L, already shows A. Here's a property of the material. That's a constant. So for the spring equation is force times spring constant times change in length. Now you know that change in length is EA divided by L. All right, hell yeah. So those are the answers, and we can go right to the back of the book. But I was happy about this one. It's so interesting that the plastic problems are just like, oh yeah, and find the point where it goes plastic. Well, basically, you're just saying that these have a max force, and the whole thing is just a statics problem. So they definitely say that in the textbook. They're just like, yeah, once every material or the material in questions hit that plastic load, you just treat it like a force that is unchanging, and then it just becomes a statics problem. 212.9, and let's get the hell done with this one and be done for the evening. So 212.9. Okay, 212.9, we have that yield force. 212.9, oh, what the hell? So determine the yield load Py and the corresponding displacement delta y at point D. Determine the yield load Py and the corresponding there was two aspects of this problem. So the second part is kind of what I solved. It was, and I guess we're going to have to talk about that. So we have they wanted to know the yield. That makes sense. I get it now. Because I was just going right for the plastic problem. You know, turn that one plastic and turn that one plastic, and that's what we did. So we found the force plastic. And so they wanted to know, and so that was 5 force yield stress divided by area. So we got that, and that was a distance of 2 yield stress L divided by E. Okay, so let's talk about what the hell they wanted, and give them what they wanted. They said, hey, we're gonna make sure everything is stretched out, but once P is small enough to when we would let go of P, every molecule in these cables, let's say, go back to, or the rigid bars, go back to, or steel wires. These steel wires, every molecule goes back to their original shape. Okay, so we're going to have that geometry, and we're going to realize that, oh hell yeah, this is the limit right here. And we already know from our equation that, change in length is FL over EA, and then I can say that FA is yield stress length divided by E, and I'm going to say the length is 3/4 L, so I can say the change in length of this is going to be 3/4 delta YL divided by E. And if that's the case, this is the point where once this gets stretched out, we know that it hasn't. This one hasn't gone plastic yet. It's right at the yield. Cool. And now we need to know the force in this one. Well, we know if this is 3/4, we know that this is 2/3, so we do that same thing, 3/4 times 2/3, and we know that this is half. So the change in length of that one, again, now we're just cooking, is this. And once we know this, then we can, well, how would we find the force in this chord? We would say also that this is equal to FL divided by EA. And isn't that right? Because if we find the change in length, I mean, you basically say that change in length is FL divided by EA. And you solve for F. So you go F is equal to change in length EA divided by L. Okay, cool. And now we just need to make sure when we divide by L, it's this length or that length. So we're trying to find BY, and that's going to be F, and that's going to be this change in length, which is 1/2 sigma y L divided by E, times EA divided by L. So all that cancels, and we're left with 1/2 sigma YA. Now, that was probably a roundabout way to do it, but that's fine. I'm sure there's a simpler way, but hell no. I just write all the equations. You know what I mean? Just get good at just writing all these, and then the relationship, and then putting them all together. So you got FA is equal to E change in length over L, and then this, out of these 5 characters, you can rearrange them however you want. Okay, so now that we know BY is 1/2 sigma YA, we know that this is up to the yield, so CY, you know, just by now knowing what the hell's going on, is just the yield stress area. We've already done that. And you could do it in reverse. You could say the change in length of C is 3/4. We could do the same thing we did for BY. You could say that's 3/4 yield stress L divided by E, and we're going to say that's the change in length. So now we're going to take that change in length multiplied by EA divided by, well, now you got to divide by 3/4 L, and then there you go. Those cancel, E's cancel, and now you're just left with, and the L's cancel, sigma YA. So you probably slow down the video for that one, but that was good because now you know the force there. And now you go back to your free body diagram. P at C you have you know, that full load, and then here, well, you just have half. And now you got A. But we just take the sum of the moments about A. That's the only equation that we need is 0. So we're going to go 1/2 sigma YA. Alright, hell yeah, home stretch. And if you want to do the faster way, well, we're going to have B's on, you know, we're going to have this B term on every term, so we can just get rid of it. So we're going to have 1/2 sigma YA times 2. Cool. And then plus, this is sigma YA times 3. Cool. And then minus, then we're going to have 4P. Cool. And that's going to be equal to 0. So might as well just equal it to 4P. And this is just sigma YA. And so we're going to have 4 sigma YA is equal to 4P. And now you can see that P is sigma YA. So that was that problem. We know that the... but they also wanted to know the delta D. So we said that if this was 3/4, then this thing, if this is a quarter, this is a half, this is 3/4, this has to be 1. So the delta D is, what the hell was the change in length? It was this. So delta D was sigma Y L divided by E. So there you go. So I'm going to write it one more time. Delta D is sigma YL divided by E. And there you go. So we did it. We did the at the yield and then at the max. And so go to the back of the book. And yeah. You know, sometimes these aren't worded well enough to ask you. I mean, I guess I didn't even read it. So there you go. The yield load P, sigma y, A. So yield stress times area, and then the change in length at D was the yield stress L divided by E. So that's what we got. All right, hell yeah. And man, do we have time to draw a load displacement diagram? I guess, you know what I mean? Might as well. Might as well. So what they want is, you know, as this gets displaced, we want to know the load P. So draw a load displacement diagram with the load P, and as ordinate, which is in the y direction, and the displacement D is the I had to look that up. It's in the x direction. So we're gonna go booyah, and let's write down. You know, let's write down the yield. So we have delta yield is equal to sigma YL divided by E. P yield is sigma YA. And then we have delta P. That's going to be that max. We solved for that first. Delta. This is going to be 2 sigma YL divided by E. And then you have the plastic load P. And that's going to be 5 force sigma YA. So hopefully this should be fairly simple. So we're going to put the load here, and then the delta here. And then so for the delta, we're going to have 1, 2. Cool. So we're just going to do 1, 2. And this one we're going to have up to 5 force. So we're going to go 1, 2, 3, 4, 5. Cool. And then, so no load, no displacement. And then as we put the load on, these are like two springs. And both of them are always, you know, a spring is always linear. You know what I mean? So if both of these are springs, hell yeah, they're acting at the same time. You could say, you could replace both these springs with one spring in any location you want. You could replace both these springs with a spring right here directly over P, and it would still make sense. But yeah, two springs can be replaced by one spring. So that's why this line will be just linear. And so we're going to say, so right at this point, we're going to be all the way up to, and this is basically 4 over 4. Yeah, so this is cool because it shows how both these are doubly strong, but the second one goes plastic, it's like it just dropped out. It's like not helping you anymore. Okay, so we're going to have 1, 2, 3, 4. So this is 4 over 4. This is 5 force. And so we're going to have a load right there. And then once we go to 2, so this is delta YL divided by E, and this is 2 delta YL, sorry, sigma Y. It's yield stress. It's so hard for me to remember that. And then this is yield stress area. Cool. So once we get to 2, we're going to go up to that 5 force. So there it is. I think this is, no. But yeah, we go there, and then once this drops out of the sky and it doesn't do nothing, you know what I mean? Because then you would have a discontinuity, where, you know, or I don't know how it would look, but this is still it's still holding this force, but that's all the force that it can hold. You know what I mean? It's holding sigma YA, but no more. And so that's what we have. Once that hits sigma YA, that's interesting. Because the yield force is sigma YA. I guess that's right. The P to yield this is the same as just one of them. Okay, cool. And then we and then you can only put just a little bit more before this other one maxes out. And then after this point, it just goes. You can't take any more force. If you try to put 6 force, sigma YA, you can't do it. It'll just go plastic on you. So there you go. But like I said, these change in lengths right here are small. You know what I mean? They're a fraction of like 0.2% if it's steel, and steel can stretch another up to 5%. You know what I mean? So let's do that. That's always a good one to do, because if we're like at 0.2% is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 0.01. This is 1%, and then we'll go 2%, 3%, 4%, 5%. So here's your graph. This is what your graph would look like. You know what I mean? This is the elastic, and then this is the plastic. You know what I mean? So a material can be plastic if it's steel up to like 5% stretch. And so this part and this part is literally just kind of right in here. So this plastic part can just kind of go off the page. You can go plastic for quite a while. All right, hell yeah. So I think that solves it. You know what I mean? Some of these things have like multiple steps. They'll go like this, and then back to, you know, something like that. But this one, I think I'm accurate on that. You know, I don't see any other points. Like you're going, like I said, you're going to load these up and it's elastic until this one, you know, craps out. And it's still going to take the same load, but then this one is the only thing that's allowed. That's why this really shallowed out. And once this maxes out, hell, this is just a straight line all the way across. All right, we did it. Plastic problem, 1 star. And we learned quite a bit. And the take-home point was, yeah, change in length is FL over EA. Circle the F and the A, and you get yield stress. Hell yeah, getting better at saying that, divided by E. That was the equation that was useful. And then obviously force is equal to, you know, yield stress times area. And that just makes sense. Pounds per square inch times square inches. Cool. And this is pounds per square inch. This is pounds per square inch. So those cancel unit-wise, and then you're just left with a unit of length, which is change in length. All right, hell yeah, I'm ready for being done for the day. So thanks for joining me, and guess what? That's a video. All right, holy Toledo. I went to go to make the movie, and I totally forgot about our check on reality. Because didn't we say, hey, if these are 1 inch, you know, steel rods, you know, and we thought if the P was underneath them, it would be 2 times 58, which would be 116,000 pounds. So what can we put a load P? So we're going to say that the plastic load is going to be 5 force times the yield stress of the area. So it's, you know, if this was directly underneath, plastic load would be 2 times the yield stress over the area, but it's not. It's just 5 force. So we're going to go 5 force times 58,000 psi times 1 inches squared, and we're going to get 5 divided by 4, 1.25. So 1.25 times 58,000, and we could only put 72,500 pounds. So I was off. Like my guess was somewhere. My guess originally was like 9,000 pounds. And obviously, so here was my original guess of 9,000. But that's why you do that, you know what I mean? That's why we took the problem and put a little bit of realness to it, you know what I mean? And so most things are going to be made out of steel and material mechanics problems. Steel or concrete, those are going to be your 2. Sometimes made out of aluminum, but those are kind of the more, you know, trickier problems. Not necessarily tricky, but sometimes the stress-strain curve does this, and it's actually elastic still in this range. It kind of bends in a curve. But anyway, hell yeah! So we put some numbers to it, and we got that if these are 1 inch steel, you know, shafts or whatever, bars, you could only put a P of 72,000. Even though you got 2 of them, and you know that they could both, if you put the loads right underneath them, you could get a load of 116,000 pounds out of each of those, which again would be that delta YA, which we've talked about. Okay, hell yeah. So that does it. That actually puts a real world analysis on it, and I'm glad I caught myself. So anyway, thanks for joining me, and guess what? That's a video.